Welcome to another tutor short provided by the Educational Support Services Department of Lehigh Carbon Community College in Snexville, Pennsylvania, which is just outside of Allentown. These videos review key learnings for the science courses provided here at LTRI-C. And please remember that the Educational Support Services Department does provide walk-in tutoring 5 days a week. Today we'll look at balancing chemical equations. To do that, I came up with this example problem in red. Write the balanced chemical equation for the creation of iron 3 oxide from iron and oxygen. When you start at this basic level, you actually need to do a few steps before we actually get to balancing the equation. But it's a good way to start. So you would look at this problem, and you should start with saying, okay, I'm going to take iron, which is Fe, and somehow I'm going to react that with some oxygen, and I'm going to come over and make some type of iron oxide. Iron oxide should be able to say, well, it's obviously going to have some iron and oxygen in it. So you sort of start with what atoms are we talking about and which ones are combining into molecules. So that's what I would call the first step. The next step is to see, well, do I have these in the right form for a chemical equation? Iron is a metal and can exist by itself, so the iron here looks fine. The oxygen, though, should have sort of, I'll say, rang a bell in your head. And oxygen is one of the diatomic gases. The diatomic gases are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. The diatomic gases in nature always exist as two atoms together. So again, for oxygen, that means up here, oxygen, if we're reacting it, would be an O2. Same, and continue down here. These are all the diatomic gases. So whenever you're reacting something with one of these elements by themselves, then you have to use two. Okay, so now we have oxygen in the right form. And now we look at what we're making over here, the iron oxide. So we know we're trying to make iron 3 oxide. You should recognize that because it's iron 3, it means iron is one of the transition metals, and that the charge in this form is going to be a +3 charge. So the iron ion in this ionic molecule here has a +3 charge, which means it wants to give away or transfer 3 electrons. Oxygen, an ionic bond, should be aware, is a -2 charge. So if we just have a molecule in this form, one iron with one oxygen, you notice it doesn't balance. You got a +3 electrons and a -2, charge here. So you end up with a +1, meaning an extra electron that doesn't have a home. The iron is giving away 3 electrons. The oxygen can only take 2, so there's 1 left over. And that's not allowed in ionic compounds. It has to balance out to 0. You have to have an equal balance here of electrons. So you're probably familiar with a trick called crisscross. That if you have a compound like this, you take the charge from the one on the right, this oxygen here on the right, it's a 2. You bring that down as a subscript for the iron, and you take the charge of the iron to 3, bring that down as a subscript for the oxygen. Now what that does for you is now we have 2 irons, each one with a +3 charge. So that means we have a +6 charge here, or essentially 6 electrons that the irons are giving away. And the oxygen, each one wants 2 electrons, and we now have 3. So therefore, the oxygens can accept 6 electrons, -6 charge, and now we have a balance, +6 and -6. So iron 3 oxide looks like that, Fe2O3. Let me get rid of the extra charges here. You don't need to see them anymore. Now we're at the point where we have the appropriate molecules and atoms in our equation. Now we're at the point where we can balance the chemical equation. I have a list of hints that will sometimes help when you're trying to balance an equation. And I'll bring that up right now. Bring it down here. Okay. So let's walk through those. The first hint I have is to leave single atoms and diatomic molecules for last. And that's because they're generally easier to balance because there's either only one or just two of them. So if you need 3 irons, you can just put a 3 in front of the iron here on the left. If you need 6 oxygen, you can put a 3 in front of the oxygen here and get 6. So try to leave the ones that are single or diatomic for last because they're a little bit easier to balance. The second hint I hear is to treat polyatomic ions as single atoms. I'm not going to do that in this example, and I've actually made a separate video on how to do that. So take a look at the videos listed under L-tri-C here, and you'll see one that says balancing chemical equations with polyatomic ions. You can take a look at that. The third hint is to start with the most complex molecule. That'll normally get you a long way towards the answer. And then fourth, if you come up needing a partial atom or molecule, if you come up needing like 1.5 of some molecule, then you can balance the equation by multiplying everything, in that case by 2, and you'll see that it will help you balance out. And the example I have here is going to fall into that, so we'll see how that works in a minute. And then if these 4 don't help you, really all you're left with is guessing, and sometimes that's where you'll end up. Just try to throw a number somewhere, work it through, and with trial and error you'll be able to solve the problem. So let's walk through balancing this one now. Example the hint number 1, we're going to leave the iron and the oxygen on the left for last. That leaves us only with the iron 3 oxide to start with. Number 2 here we don't have, so skip that. Number 3, start with the most complex. Well, we are. The iron 3 oxide is where we're going to start. And then we'll see with 4 whether we end up needing if there's any partial atoms or molecules. So let's start here on the right. We're starting with iron 3 oxide. We'll start with the iron first. We have 2 irons on the right here. So let's look over on the left. We can put a 2 here, and that gives us 2 irons on the left. So now the iron looks okay. Now we look back on the right. After we did the iron, now we're going to look at the oxygen in iron 3 oxide. We have 3 oxygens. We go on the left, and we see oxygen, though, is diatomic. There's 2 here. The only way for me to get 3 oxygens out of this is if I put up here, instead of a whole number, 3 halves. You think about that as maybe 1.5. If I had 1.5 O2 molecules, that would give me 3 oxygens, which would balance with the 3 oxygens on the right. But I have a fraction here. All these numbers in front in green have to be whole numbers in order for the equation to be balanced. So now we can use this hint number 4, which is to take a look and multiply everything by a common number. And the reason I showed the oxygen as 3 halves is that sort of tells you what do you need to multiply by. If I multiply all of these by 2, you'll see 2 times the 3 halves will give me 3 O2s here. So let's start from the left here. 2 times 2 irons, we need 4 irons. We do the 2 times the 3 halves, you end up with 3 O2s. And then for the iron 3 oxide, you just put a 2 because this was a 1 before. Iron 3 oxide is this. Okay. Now I think, if we're lucky, this should have balanced the equation. So let's start. Let's look here. We have 4 iron over here. and we look over here and we have 2 times Fe sub 2 here. That means we have 4 irons over here. So we're okay on iron. We look at the oxygen. I have 3 sets of O2, so that's 6 oxygen over here. And now I have 2 molecules of this. Each one has 3 oxygen. It means I have 6 oxygen over here. So now we're balanced. The irons are 4 on each side and the oxygens are 6. So this is our balanced chemical equation. As I said, please take a look at our list. We do have another separate video on how to use polyatomic ions, and that'll help you when you get involved with those. Thank you.